So welcome. So we're going to talk about the laws of motion today. And basically the laws of motion are all about Newton's laws. And what we're going to say is, well, we're going to begin with the concept of force. We're going to talk about Newton's laws about force. We'll clear up some confusion about inertia, mass and weight. And then we'll start looking at two or three big things, really two things. And that is equilibrium and non-equilibrium. And that is the formation of statics and dynamics. And for those doing engineering, there's a famous statics course, which is a gatekeeping course, and goes on like that. So we're beginning to get to some of the serious stuff. Force is a very interesting thing. A net force causes acceleration. And if you have acceleration, you must have a net force. And you feel acceleration. You don't feel velocities. You can be going as fast as you like and you won't feel the velocity. If there's jostling, if there's turbulence, you feel it. But you don't feel velocity just because. You can be asleep on a plane traveling at 500 miles an hour across the Atlantic and you're just sleeping like a baby because it's a nice smooth flight. You don't feel that motion. The problem we have is that because we live in a friction-filled world, we tend to associate forces with motion. We've learned that when you stop pushing, things stop rolling. And that is a really unusual occurrence in the universe. In the vast majority of the universe, when you stop pushing, things stop going faster. They'll keep on going forever. But on the Earth, because we have friction, then that's not the case. So as scientists, we've got to break ourselves of this linkage between motion and force and make the linkage between acceleration and force. And it's one of those things, it's a bit like combing your hair where you do it and it's really painful. And if you don't do it again, it's going to be really painful every time you need to do it. But if you recognize I've got to break this link between motion and force and make the link between acceleration and force, if you keep on doing it bit by bit by bit, it becomes second nature. But you're trying to undo the perception of a lifetime. So when you're stressed, when you're tired, when you're not quite thinking, it's going to go back to the old way of thinking. And so you've got to groom yourself to try and avoid that. And I remember having a conversation with a book publisher, and I just made that mistake. And it was one of those things where as soon as it was out of my mouth, I knew, oh man, that's backwards, and you can't take it back, and you can't unhear it, And the guy was nice enough just to smile politely and then left, But So let's think about forces. Now, again, we've got to be there's a little bit of insight here that we might not start off with. Okay, so we talk colloquially. So I can talk about a contact force or I can talk about a field force. And the field force sounds really, kind of like Star Trek, If I said to you, we're going to study invisible force fields, and you went home and told your parents, I'm going to study invisible force fields, they'll go, do they do that kind of thing at HCC? I thought they only did that kind of thing in, big universities. Invisible force field is gravity. It's like we're just so used to it that it doesn't impress us anymore. But when you think about it, how does this pen know where the desk is? It's a piece of plastic. It doesn't know. Look, I can confuse it, okay? And it never makes a mistake. If I showed you where the windows were and put you in a chair and closed your eyes, so you didn't have eyes like the pen doesn't have eyes, and then spun you and then said point to the window, you would not point to the window. You would have no idea where the window was until you open your eyes. But the pen always knows where the earth is. How on earth can the pen know where the earth is? This is amazing. This is like magical. We can say it's gravity, but I could say, yeah, it's actually Frederick. It's like, it's a name. It doesn't mean anything. Gravity, it's just like kicking the can down the road. How does it know where the earth is? You can say, well, Albert Einstein says there's a curvature of space-time. Well, yeah, okay. But that's also, Do you want to know what a particle physicist says? particle physicist says that there's an interaction between gravitons emitted by the pen and gravitons emitted by the Earth. It's a bit like having two skateboarders going side by side. And they're traveling side by side, and then one of them takes a backpack and throws it to the other. And of course what happens is as this skateboarder catches it, it veers off to the top, and as this guy throws it, it veers off to the bottom. And so there's a repulsive effect between these two skateboarders by the transfer of an intermediary particle. Okay? And that intermediary particle is like the graviton, say, you know. Well, it turns out that this is a repulsive force. It's a lot harder to explain an attractive force, but it's the opposite. We'll say it's the opposite, okay? Can I have a bucket full of gravitons, please? Oh, we haven't found any yet. Okay. Will the pen ever run out of gravitons? No. They never run out, and you can't show me any. Am I supposed to believe this? And the answer is, to the extent that it works, yes. You know, why not? If it gives you the right answer. But do you really? But is it literally true? I have no idea. So this is like magical stuff. This is like when you ask about fundamentals of physics and engineering. It's deep. And maybe we'll never truly know what happens. And maybe as engineers, we don't really care. It's like, you know, I don't really care if there's gravitons between the top of my bridge and the ocean. I don't really care. All I care about is, will it stand up when cars drive across it? And that's good enough. Well, okay, if our model is okay, our model is okay. But we need to think a little bit deeply to make sure our models are okay. And so we have these ideas of contact forces and field forces, and the good examples are touching or pushing or pulling. They're all contact forces. And gravity and magnetism, electrostatics, they're all field forces. Field meaning non-touching. You know, there's a field around the Earth which causes the Earth, the pen to be attracted to it. But it's not touching, whereas when I put my pen on that table, oh, it's touching. And just to kind of give you a bit of a, you know, bit of forewarning, nothing in the pen touches the table. If the electrons of the pen ran into the electrons of the table, we'd have a tough time. The electrostatic forces, again, are pushing those things apart. So what we have is a short-range electrostatic force keeping another short-range electrostatic. It's the force between those two electrostatic forces. So even these contact forces are really short-distance field forces. But it doesn't matter. Colloquially, we can talk about contact forces and field forces. But now, let's look at these things. Let's think about the Earth and the Moon, because it's a kind of good visualization. Now let's think about the apple and the Earth. Or the pen. Let's think about the pen and this. Pen and the Earth. The Earth definitely pulls on the pen, yeah? It's not so obvious, but the pen also pulls on the Earth. The reason why it's not so obvious is because the pen's really small. So the pen shows the effect, whereas the Earth doesn't. But when I drop the pen towards the Earth, I literally move the entire Earth towards the pen. It's such a small change because the mass is so big that no one can measure it. But these guys meet. It's not that the Earth stands still and that one goes down. These guys meet. But the motion for the Earth is so small, it's unmeasurable, and the motion for the pen is so obvious. So there's a symmetry here. There's a symmetry. It's not a symmetry of motion. It's a symmetry of force. To get any force, you have to have two objects. And you cannot have a force, you get two forces. It's an interaction. A force is not really a thing. It's an interaction. I push on my glasses push on me. If my glasses. Don't push on me. I can't push on my glasses. It's an interaction between the two. So they always come in pairs. The pairs are always equal and opposite in terms of force. And if I only have one object, I can't have the force. I need two objects for gravity. I've got to have two objects to have the force. So we say forces come in pairs, mediating between two objects. A force is a vector quantity. It's got a direction and a magnitude. If an object has several forces acting on it, the forces combine to give a net force. If I have a billiard ball and I pull it in three directions, I don't get that. It doesn't become like chewing gum and get stretchy. It always stays as one object, and all that happens is it feels the net effect. It feels the overall effect. It doesn't know there's 3 or 5 or 7 people pulling on it. It just goes, I feel a force in that direction. And so it happens. So in a way, that's a simplification. So Galileo did a lot of work in this, and he did a lot of experimentation. Galileo was a remarkable person because he was able to take friction out of his experience. And when we get to a bit later, we'll get to some of that, and it's just fantastic what he did. He's a very, very smart person. He was an experimentalist, and at a time when there wasn't really a tradition of experimentation. But 50 years later, along came Newton, and Newton was one of these scarily bright people. I don't know if you ever have this hankering to be kind of like famous and successful. And my only caution to you is be careful what you wish for. My wife says this is sour grapes. But I like to read biographies of famous, successful people. And, oh man, there's always a price they seem to pay. I don't think you can do something that is talked about 400 years later unless it is a bit obsessive for you. You don't get remembered for going, me too. You get remembered for saying something that's outlandish and you're right. And to have that kind of insight or that kind of thinking, you don't get that just casually over on a Sunday afternoon, kind of like daydreaming. You get that because you've been sweating it for most of your life. And Galileo had his issue. I thought Galileo was pretty well-rounded person. Galileo just never married his wife, basically. They had several children. He just never married her. His children then had no standing in the community. So his children could not marry because Galileo didn't marry their mother. That became a bit of a problem. So Galileo decides that the thing to do is to have them join the church as nuns. Well, the church, back in those days was not kind of like a repository for famous people's kids. You had to get to the age of maturity and then basically sign up for the church as if you were getting married. It's basically as if you're getting married. You're marrying the church rather than a person. And Galileo was trying to get his daughters in there when they were way too young. And there's letters that have survived in which the Mother Superior is going, these children, they're not mature enough to make this decision. And he's writing back going, oh no, they're really mature. No, just talk to them. They know what they're doing and all that. And you read that and you go, especially having a daughter myself, it's like, I couldn't imagine turning around and just going and saying to somebody, oh, take my daughter, man, you better take her because she's got no standing. And so you look at that and go, what was he thinking? He was, in my opinion, he was busy writing his books, And then Paul Newton, I don't think had a friend in his life. He basically would wait in his little office until the cafe had emptied. And he'd be the last person in line. He'd get his food and take it back to his room. He spent 10 years doing physics. He spent the next 10 years doing alchemy. He spent the next 10 years doing communing with spirits. His first 10 years made his name, you know. He developed feuds. If you crossed him, he basically would destroy you. He had no family. You know, his childhood was not very nice. He was basically, his dad died, his mum remarried, his mum's husband did not like kids. They moved into the city and left him on the farm. And then when he got old enough to go away to school, he went away to school and they moved back on the farm. So he spent his whole life kind of like missing his parents to some extent. I mean, this really tough situation. But in the end, I read this article one time, and it said the difference between being really bright and being a genius is if you're working on your thing and you're really bright and somebody comes in and says, your mother's sick, you need to come and see her, you put the pen down and you leave. That kind of genius, the price you pay for genius is if you're working on that and somebody comes in and says, your mother's sick, you say, oh, just give me a minute, and because it's all about that. Maybe it is sour grapes, I don't know. But Newton 400 years ago, we're not just talking about him, we are reading his books. In optics, it's like the same language he invented. The guy was amazing. So he looked at what Galileo had done and he said, oh, these are the principles. He was able to codify these things. And the first two laws are kind of the same. It basically says, if there is not a net force, then you don't accelerate. Accelerating meaning changing your state of motion, meaning speeding up, slowing down, or going round a corner. That's acceleration. So if there's no net force, you can't do any of that. You can't speed up, you can't slow down, you can't go around corners. If there is a net force, you must speed up, slow down, or go around a corner. And in fact, it's the net force is equal to the mass times the acceleration. Mass is very abstract. It's not really the same as weight. And then his third law is, for every action force, there's an equal and opposite reaction force. I push you only as hard as you push me. When somebody hits me on the jaw, my jaw hits their fist just as hard as their fist hits my jaw. The outcome's different. It feels really bad for me, not so bad for the fist, but the forces are the same. So these really kind of amazing insights. We have to deal with the first two to begin with, and we've got to be a little bit careful about just building our visualization. We've got to be good at saying what acceleration is and recognizing when it's taking place. Because it's abstract. It's a change of velocity. It's a speeding up. It's a slowing down, or it's a going round a corner. It's any of those. You can speed up and change direction. You can just speed up. You can slow down and change direction. You can just slow down. You can just change direction. They're all acceleration. So if I see a change in speed and or I see a change in direction, I know I've got an acceleration. And if I have an acceleration, I must have a net force that causes it. And a net force is not any old force. It is the overall force. So in one dimension, I'll take the force to the right, I'll take the force to the left, and I'll sum them vectorially. So let's go to the next level. There's no net force. So there cannot be an acceleration. So you cannot be changing your speed and you cannot be changing your direction. No net force, no acceleration, cannot be changing your speed, cannot be changing your direction. If there's no change in speed and no change in direction, there cannot be an acceleration, so there cannot be a net force. So these things link together. And kind of like if I tell you that bit, you can infer that bit. If I tell you that bit, you can infer that bit. If I tell you that bit, you can get the middle bit, and so on. They all go together. On the other sense, if there is a net force, there must be an acceleration. And that means there must be a change in speed, or there must be a change in direction, or both. But there's got to be something going on. You can't just have nothing going on. If there is a net force, there is an acceleration. So either one or both of those must be taking place. And if either one or both of those is taking place, there must have been a net force to cause it. And that's just not, we're not used to thinking at that kind of level of it, so it's sometimes hard to interpret from a picture of a journey what's going on. So let's practice. Baseball player hits a ball into the outfield. If the action force is the Earth's pull on the ball, what is the reaction force? I'm so sorry, I'm going to turn that off. That's interesting. So a baseball player hits a ball into the outfield. So baseball player hits a ball into the outfield. If the action force is the Earth's pull on the ball, force of the Earth on the ball, what is the reaction force? Yeah. Ball on the Earth. So, I'm sorry, ball on the Earth. So this is action-reaction pair. Did I just skip a slide? No, I didn't. Okay. So it's got nothing to do with the baseball player hitting the ball into the... That's just like red herring. Action-reaction pairs. The force of the Earth on my hat is equal and opposite to the force of my hat on the Earth. The force of my hand on your chin is equal and opposite to the force of your chin on my hand. You just get the two objects and reverse them. Action-reaction pair. Big mass on little mass is the same as the force of the little mass on the big mass. We should really name these things with the two objects, but we don't, do we? We talk about weight. We should talk about the force of the Earth on, the pen. But we talk about weight. It's shorthand, it's colloquial, but when we begin, it can lead to some issues. Plane is flying straight and level. It's got a speed of 150 miles per hour. It's constant speed. It's cruising. That's what cruising means. Cruising means you've got a constant speed of 150 miles per hour. And then which statements are correct? Plane is experiencing a net horizontal force. Plane is experiencing a net vertical force. So we're dividing this up into two directions. Are both correct or neither? I'd like you to think about it and commit. I want you to decide. I'd love it if you wrote it down, but if you don't want to write it down, just in your mind, just decide. And then I want you to talk to the person next to you or around you and just see if you both agree. Okay, so just, hey, I think A, I think B, I think J, whatever. Just see if you agree. The trick is the language. You're in air. You're in air. This is not a projectile. This is a plane. You're in air. So. Give you another few seconds. I think I cut you off. So, let's think about this. Let's talk vertically, first of all. Is there an acceleration vertically? There's not. Why is there not? What is it that tells you there's no acceleration vertically? Vertically. Straight and level. Straight and level. To go up, you've got to change your speed. To go down, you've got a vertical speed. So no acceleration vertically, so no net force vertically. Agreed? No acceleration, no net force. What about horizontally? Is there an acceleration horizontally? Is there a force horizontal? Yeah, there's two forces, isn't there? There's a force to the front, which is the thrust, but there's also air drag. Otherwise, if there's no air, you don't fly, you know. So there are forces, but there's no net force. So net force does not mean no force. It means whatever forces are there cancel each other out or add up to whatever the net force is. No net force means no overall force. There are forces, but they're cancelling each other out. So we have the force of thrust, we have the force of drag, and these two must cancel each other out because we're at a constant speed. If we weren't at a constant speed, there would be an acceleration and there would be a net force. So experiences a net force horizontally. There is a force horizontal, but it's no net force. So neither one of those two is right. So D was the best choice in that one. There's neither a horizontal net force, nor is there a vertical net force. Yeah? Cool? Yeah. Car is cruising at a constant speed of 50 miles an hour around a large circular track. Does the car accelerate? And what, if it does, why? Because does it accelerate in the direction of travel? Is it in the middle of the track? Is it towards the outside of the track? Or is it not? You know, is the acceleration there? Or is the acceleration there? Or is the acceleration there? Or is there no acceleration? And again, decide what you think. And then see what you think. So the answer is going to be towards the middle of the track. It's B. So first of all, we know it's one of those three because there is a change in velocity because we're going around a corner. And if there's a change in velocity, there's an acceleration. So we know that happens. Then the question is, which one of these three is it? And if we're accelerating in that direction, then our speed changes in that direction. But it says at a constant speed. So that's not going to be right. So it leaves these other two. And it's actually, we've not actually done this section yet, so it's a bit of an unfair question to take it as far as this. But does anybody know what this kind of acceleration is called? Yeah, this is centripetal acceleration. And this would be, they sometimes call it centrifugal acceleration, but that's a fictitious acceleration. It's like, it's an acceleration that doesn't exist. I can show you that this is towards the middle, because if I go like that, and that's my VI, and that's my VF. They're the same size, just different directions as I go around the track. And if I say VF minus VI equals my acceleration, because that's what acceleration is, then I do my VF, and I add on to it minus VI, VF. I add on to it minus VI, and so my resultant is pointing towards the middle of the track. That's where that comes from. It comes from circular motion. We'll get to that later. So I hope you got the fact that there was an acceleration. It was really nice if you got that it was B, but it's not the end of the world if you didn't, you know. Let's put some numbers. We have a 1 kilogram block. I always put my masses inside the block. I put my forces on the end of arrows, just shorthand. I tend to put my velocities to the side of the block. So my velocity would be like that, and my acceleration would be like that, but my forces would be like that, and my masses would be like that. That's just my shorthand for my diagrams. It just makes it kind of like nice and neat for me. And does this object accelerate? Well, divide it into vertical and horizontal. The sum of the forces vertically equals +2, because that's upwards, plus -2, because that's downwards, and that equals 0 newtons. If F equals ma, 0 equals 1 times a must equal 0 meters per second squared. So it's not accelerating horizontally. You can kind of see that, can't you? They balance each other. So I'm being a little bit pedantic in this. Horizontally is equal to +5 added to -3, which equals +2. Sum of the forces equals ma. +2 is equal to 1 times a, so a is equal to +2 meters per second squared. Oh, that means 2 meters per second squared to the right. So we're unpacking this thing. We're looking just like we did with the motion. You look in your x direction, you do your stuff. You look in the y direction, you do your stuff. Then you can figure out from there. But I'm not going to put that 5 with one of those 2's because they're not in the same direction. So I'm thinking in terms of axes as I go through this. If the student pushes on the wall with an action force of 10 newtons, with what force does the wall push back? 10 newtons. I lived in Boston for a while, so I actually had experience of this. You get up on a nice summer's day and you jump in your car and you turn on the engine and you put your foot on the gas and you take off. And you get in on a cold winter's day and you turn on the engine and you put your foot on your gas and you just stay there. The car's making a whole bunch of noise and you're just staying there. You're doing the same thing you always do. The car's doing the same thing it always does, but there's a different outcome. Normally a car pushes the road, that's an action force, with 100 newtons. And the road pushes, that's a reaction force, with 100 newtons. On an icy day, can the car push the road? The first bit. Can you push the road with 100 newtons?
Does the ice equal 0 friction?
The ice equals 0 friction, yeah. And the answer is no, you can't push. And that makes no sense because if I'm doing what I'm doing, then I must exert the force that I exert. I mean, my gasoline's been used, my engine's turning, the vehicle is doing everything it does. So surely the force that it exerts must be the same. But forces are things like that, they're interactions. And although my engine is turning, I'm not generating a force because the road's not playing back. So the force does not depend upon you. It depends upon you and the other object. You can't have a pull on the moon independent of the Earth. The Earth is involved. And if there's no Earth, there's no pull on the moon. And if you want a graphic example about that, then, you know, go to the gym and practice and practice and practice, and then step to the wall and do the same thing. And the outcome's completely different, isn't it? And this really hurts, and that doesn't. And in this case, I'm not exerting any force, I've just moved my arm. And until something resists, there's no force. There's motion, but there's no force. And in this one, there's resistance, so I feel the action-reaction pair. So it's getting rid of this idea that the force is all about me, or all about my car. It's about two things. And there's this Action-reaction pair to it. So this is, no, you can't generate, you can't create 100 newtons unless something pushes back. I had a boss in North Carolina. I had a boss who I didn't get on with. And I had a Russian student who was a bit zen-like. He was an interesting guy. And as things were going downhill with my boss, there'd be like conflicts. And when the boss would go, my Russian student would say, Tony, he'd say, be like a reflecting pond. Reflect the hate. Just reflect the hate like that. And I go, oh man, I can't do it. He goes, it's like Newton's laws. If you don't resist, he can't resist. It's true. If you're nice, everything's going to be nice, but it's hard to do, yeah.
That would be true if it was like a studded tire, though, right?
If it was what kind of tire?
A studded tire.
As long as there's no friction, whether it's studded or not, you can change the shape of it. All the stud does, it means you got more friction. But in principle, if I can have studded tire with no friction, maybe you can argue and say you can never do that. But if I can do that, then, you know, I can, doesn't matter. The key thing is, it's the frictional effect which enables the action-reaction pair. It's how much the road is prepared to push back. You know. So here's some interesting things. So a pickup truck. Have you ever seen these things where, you know, somebody breaks down, so they phone up their buddy and they say, can you push me home? So we have a pickup truck and a car. And they're on 75 and 275, straight and level bit, and they're doing 50 miles an hour, just like steadily. So here they are, they're doing V equals 50 mph, and it's a constant speed. A constant, so you can say A is equal to 0 meters per second squared. I want you to compare the force of the pickup on the car with the force of the car on the pickup. Now they're an action-reaction pair. And is the force of the pickup on the car strongest, or are they equal to each other? Or is the force of the pickup on the car weakest? For this situation, if you were to look and be able to measure, I want you to decide, and then I want you to tell the person next to you. So decide first, and then tell the person next to you. Is it A, B, or C? And then discuss why. So, the correct answer is B. Force of the... Anybody justify that for me? What's the justification?
Equal opposite, or equal opposite reaction. And the only reason we model it is because the friction on the ground.
So you're saying action-reaction pair?
Yeah.
And this clearly is an action-reaction pair, isn't it? Yeah? Okay. And, you know, it seems to make sense, yeah? But this is a bit earlier. This is when the speeding up. So there is an acceleration. You're going from 0 to 50 miles per hour. So there is an acceleration. I don't know what it is, but there is an acceleration. The thing is now speeding up. Force of the pickup on car. Force of the car on pickup. Is that one bigger than that? Is it equal to that? Or is it less than that? Now we've got acceleration. F equals ma. Got something. So now what? Decide, and then tell your nearby neighbor what you think. Now you've got acceleration. So now it's not kind of like, oh, everything's coasting. Now things are accelerating. These two forces still the same? Anybody want to volunteer an answer?
Force of the car on the pickup.
So, who thinks the first choice? Do you want to, I'll close my eyes. No, that doesn't work, is it? You close your eyes, put your hands up. Who thinks the first one? Anybody? Who thinks the second one? Anybody? Who thinks the third one? Anybody? Who's not put their hand up? Let me ask you a better question. Has anybody not decided? To some extent, all that matters is that you decide. Then you can decide afterwards, but I want you to decide.
But here's the answer.
Okay? And then I'll tell you the answer. So if you've not committed, just decide. If you get it wrong, all right, you know you've got to sort something out. If you get it right, you can cheer. If you don't decide, you have no idea. The answer is B. And it's why is it B? Because, and the answer is Newton's third law. It's the law. Action, reaction, pair, equal and opposite. Hold on. That must be in conflict with Newton's second law, because hold on, let's simplify things. Here's my two objects. There's an acceleration taking place. I need a net force. How can there be equal and opposite and give a net force? This is just craziness. And this is the example of physics is simple until you think about it. So you get a choice. Either don't think about it or accept the fact it's not going to be so simple. But if you don't think about it, you never make any progress. So you've got to go through this like valley of despair while you think about it. And then you slowly sort things out and then you get much stronger. But you've got to go through it. And this is one of those examples where, yeah, the force of the pickup on the car and the force of the car on the pickup are an equal and opposite pair. But that's not what determines the acceleration of this system. Because acceleration, the sum of the forces equals ma, is not about action-reaction pairs. It's about net external forces. And this system, this combination, these forces are internal. There's also the force of the car on the air and the force of the air on the car, and that's wind drag. And there's also the force of the pickup on the road and the force of the road on the pickup. And that's the thrust of your engine. Now, how do you accelerate? You make that force bigger than that force. That's going to accelerate. That's when you say the sum of the forces equals ma, you're comparing those two forces, not these two forces, and not these other two forces. And so can you see how, just casually, this is going to be totally confusing. We're going to have forces, and sometimes they cancel, and sometimes they don't, but they always come in pairs, but sometimes you take one half of the pair, and sometimes you take both half. So you've got to look, and you've got to visualize, and you've got to say what it is. And you kind of have a sense of it. So I'm driving along, and my car breaks down. So I got to get off the road. So I open the car door, and I lean in, and I put my hand on the steering wheel, and maybe I put my hip against the frame, and I push, and I steer myself in. I have zero velocity, I move to some velocity, so I accelerate. Agreed? My force is causing me to accelerate. F equals ma. Agreed? If I push harder, I accelerate more. Agreed? Makes sense. So when I push on the frame, or when I push on the steering wheel, that force causes the acceleration. Agreed? Well, it comes on to rain. So I sit inside my car and I push on the steering wheel. I'm pushing like I always push, but I'm not going to go anywhere. Because I just made an external force into an internal force. Because there's the force of me on the car and the force of the car on me. Whereas here, it's the force of me on the car and the force of me on the road. That's the external force coming in, yeah? The combinations of me on the road and me on the car and the car on me. And as long as I can make me on the car be external to the car, I'm going to get the acceleration. But when I go inside, there's me and the car on me, and I'm never going to get next. Pardon?
So in other words, it's a floating car.
It's a floating car. So these things take a little bit of visualization, and what I'm encouraging you to do is to say, yeah, this is not trivial stuff. This is not, let's just plug some numbers into an equation and we'll get an answer and, wait. Because they don't pay engineers to do that. Anybody can do that. They pay engineers to be able to visualize, and that involves pulling back some of this stuff and kind of struggling with it a bit. And just recognize the fact that when you do that, you are really doing, honestly, it's a noble task. It is the equivalent of committing to go to the gym and really exhaust yourself so that you'll be stronger next time. And that's the way you're going to make progress. That's what athletes know. You've got to go and you've got to be willing to sweat. Otherwise, if you just go and just, wear the clothes, it doesn't work. The only way to make progress is you've got to go through this discomfort, and there's nothing wrong with the discomfort. It's not like, this is getting hard, I'm no good at this. It's like, this is getting hard, I'm doing the right work. This is getting hard, this is a good sign, because I'm going to get through this. If it never gets hard, you're never getting through this. So I don't want you to be put off when things get, when you get these conflicts in your mind. That's a good sign, you're thinking about it. It's like, if the only thing you do is learn the equations and put numbers in, you're not thinking about it. So embrace the challenge and just recognize that even though it might seem like it gets more difficult, that's a good sign. That's a necessary thing to do so you come out the other side stronger. And just keep on with it. That question is a classic question. When I was at USF, we would recruit students from all over the world to be graduate students at USF. That's what physics departments do. And we'd get smart people from all over the world who were trained in all different universities. And we'd give them a family of questions. Just before they taught the lab, we want to see how much they knew. That combination, those two questions are classic questions. And I would say out of the graduate students, half the graduate students would get that second one wrong. And I know the first time I asked that question, I got it wrong. And I knew it was wrong, and I knew, all my gut was saying, this is wrong, but I got this conflict about Newton's second law and the first law and the third law. They're in conflict with each other, and you hold your nose and pick an answer because you know there's an issue with it. And in my time at USF, I think there was like maybe a few undergraduates would get it like that. And they were like the kind of people who'd say, it's a law! So if you didn't get it, don't worry about it. It's not, you're in good company if you didn't get it. But it's not ungettable, It's that willingness to pull back and look deeper and say, why does that seem to be in conflict with that? So this is not about, this is not about math. That math is trivial. It's about visualization of the math. Most people get into trouble because they do the good math on the wrong problem. So the more you can do to visualize, if you get your old conceptual book and just start going through it again, as you get these, now you can look with a more mature eye, you get a lot out of it. So just read around the subjects and just immerse yourself in it, and you'll get stronger and stronger and stronger. So let's call it a day, and then we'll do lab in a bit. I'm sorry I went over a little bit.